Hello, student. Hi, good evening. So today we are going to start with new topics. So that is related to what that next chapter is actually semiconductor under thermal equilibrium. Okay. So in semiconductor under thermal equilibrium, in this chapter, in this new unit, we will see first lecture about this is about Fermi Dirac Fermi Fermi Dirac Fermi Dirac probability function. Fermi Dirac probability function. Fermi Dirac probability function. Okay. So today's topic is Fermi Dirac probability function. Okay. What is this? Why it is required? So first of all, see Fermi Dirac distribution, Fermi Dirac probability function, or you can say or distribution function. Distribution function. Okay. So today we are going to discuss about this topic. Okay. So as we know very well, we are what in semiconductor. Our ultimate goal is to determine the electrical characteristic of semiconductor device. Okay. So for that, what is needed? Actually, for that we need to determine the concentration of charge carrier. Yes. So to determine the concentration of charge carrier, as we have seen in the last class, that the charge carrier concentration, these are the function of what energy level. Okay. So energy level where the electron is staying in what in different quantum state. Okay. In energy level. Okay. So therefore there we what we had done there we have found that the density of quantum state, which is a function of energy. Okay. So now actually here we want to find the electron concentration, means charge carrier concentration, through this Fermi Dirac probability function. To understand this Fermi Dirac probability function, first of all we should understand what energy level, what is energy level, what is discrete energy state, what is quantum state. Okay. So before discussing this Fermi Dirac probability function, let us first see what this is my silicon crystal. Okay. So let us say this is my silicon crystal. Okay. This is my silicon crystal. Inside silicon crystal, this is silicon crystal. There is so many atom. How many atom is there in silicon crystal? If you see inside silicon crystal, how many atom is there? 5 into 10 to the power 22 what atom per cube centimeter. Yes. 5 into 10 to the power 22 atom per cube centimeter. Okay. Per cube centimeter. And each atom, if you see, this is my silicon atom. Okay. So these are 10 electron inside. Okay. Which is tightly bound by nucleus, and these are 4 valence electron, which is loosely bound by what nucleus. Okay. So this is my silicon atom. Now see, each these electrons have their own energy, discrete energy level. Okay. So discrete energy level. Now why we are discussing this? To understand this. Okay. We will not directly jump to the energy level and finding how many number of quantum state is occupied by an electron. So that is indirect approach. So therefore, first of all, we will see from this. Okay. From scratch, because I want to make you understand first what is this energy level. Okay. So first of all, see, this many atom is there. Okay. So these are discrete energy level. What is this? This is my orbit, or orbit. Yes, this is my orbit. Orbit means what? Orbit means one energy level. This is my energy level. Okay. So this is my energy level, or you can say this is what? Orbit. This is my orbit or energy level. Now see, in energy level, inside energy level, what is there? Inside energy level, there is a energy subshell. What? Subshell. Yes, energy subshell is there. These are what? Energy subshell. Energy subshell. Subshell. Yes, these are energy subshell. How many energy subshell is there? Like S subshell, P subshell, D subshell, F subshell. Okay, SPDF subshell. But in case of silicon atom, if you will see, according to what? According to configuration, 1s2, 2s2, 1s2, 2s2, 2p, what 2p2. Yes, this is my 1s2, 2s2, 1s2, 2s2, 2p6, 3s2, yes, 3s2, 3p, 3p2, yes, 3p2. So this is what? This is my electronic configuration for what? For this silicon atom. For this silicon atom. This is what? Electronic configuration. Just we want to focus only this outermost orbit. Okay, outermost orbit, because this is what? Completely filled. Okay, this is completely filled or completely bound, strongly bound by what? This nucleus. Okay, so we don't care about this, just take care about this, which is at outermost shell, and these are what? These are loosely bound electron. Okay, so this is my S subshell and P subshell. Here S subshell and P subshell. See, this is my energy level. This is energy level. What is this energy level? This is nothing but orbit is my energy level. Okay, so inside energy level there is what? Subshell. Inside subshell, what is there? Orbital. What? Orbital. Okay, S has two one orbital, and P has how many? Three orbitals. Three orbital. Okay, so this orbital has what? Quantum state inside it. Orbital has quantum state. Okay, how many quantum state? Two quantum state. This also have two quantum state. Okay, this also have two quantum state, two quantum state, two quantum state. Okay, so like this quantum state, this. Okay, so now in each quantum state there is an electron which is sitting inside this quantum state with opposite spin. Okay, so each quantum state has one electron. Okay, another quantum state has one electron. Both are sitting in opposite spin. Yes, opposite spin. So these are what quantum state. Inside quantum state there is a electron. Okay, so now if you see overall, if you see, this is my energy level. Okay, so this is my E energy level. Inside E energy level, how many how many quantum state is there? See here, one orbital, two orbital, three, four. Total four orbital. Every orbital has two quantum state. Means total how many? Total how many orbital? Four orbital. To total quantum state how many? Eight quantum state. Eight quantum state. But electron is how much? Electron, four electron. Out of four, out of eight quantum state, four quantum state are occupied by an electron. Okay, so this is my, let us say, this is my first quantum state. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are my eight quantum state. Okay, eight quantum state in energy level. So this is my eight quantum state in one energy level. One silicon atom has what? This one energy level, and this energy level has how many quantum state? Eight quantum state. Out of eight quantum state, four are filled. Okay, four quantum state are filled by what? Electron. Four quantum state are filled by electron. Okay, so these are what? Electron. Four are filled by electron. Okay, and four are empty. Now see here, how many number of atom? 5 into 10 to the power 22 atom per cube centimeter. Okay, this we have drawn only for one atom. Like this energy level, how many energy level is there? 10 to the power 22 energy level. How many? Like this, 1, 2, 3, 4, 5, 6, dash, up to what? Up to ith energy level, which is nothing but 5 into 10 to the power 22 tooth energy level. This energy level. Okay, so this is my EI energy level. Okay, ith energy level. First energy level. Second, this is E1, E2, E3, E4, like this, like EI energy level. Okay, EI means what? 5 into 10 to the power 20th energy level. This many energy level is there within this single silicon crystal. Okay, single silicon crystal, and we have drawn the one energy level for this single silicon atom. Okay, so in order to make that is what, in order to make you understand that this is actual distribution. Okay, so before going to discuss this Fermi Dirac probability function, okay, it is must to understand first this energy level. Okay, so how energy level is formed, that we know very well. Okay, so from energy distribution, then after that, this is my energy level. Within this energy level, what is their quantum state? Okay, so within this energy level, what is their energy subshell? Okay, energy subshell. This is S subshell, P subshell, D, F, but there is only S and P. Okay, so these are what at outermost shell. Okay, and this inside is what this is completely filled. Okay, so just don't care about this. Just caring about this outermost subshell, that is S and P. S and P. S has how many orbitals? One. P has three orbitals. Each and every orbital has two quantum state. Okay, two quantum state. Total four electron. Okay, so means what? Each electron has single quantum state according to Pauli exclusion principle. Okay, every quantum state is occupied by single electron. No two electron can be allowed to occupy the same quantum state. Okay, so that is the statement of Pauli's exclusion principle. Okay, so that is for understanding purpose. We are taking the single atom. Okay, so single atom of silicon. So now see, like this energy level, how many is there? 5 into 10 to the power 22. 10 to the power 22 energy level. And how many quantum state is there? How many quantum state? Quantum state is there. Number of electron. How many number of electron is there in single silicon crystal? Means what? Every silicon atom has how many electron? 4 electron. 4 electron in the sense that outermost shell. Outermost shell has how many free? How many electron is there which are loosely bound by this nucleus? These are 4 electron. Just multiply it by 4 and it will come to into 10 to the power 23. 10 to the power 23. These are what total number of electron within what? Within 1 cube centimeter of silicon crystal. Silicon crystal means what? How many quantum state is there? How many quantum state? Total number of quantum state. If we see here, total number of quantum state is 2 into 10 to the power 23. 23 electron. Okay, per cube centimeter. Per cube centimeter means how many electron is there within single crystal? Single silicon crystal. There is total number of electron is 2 into 10 to the power 23 electron per cube centimeter. Per cube centimeter, in the sense that every electron has their own discrete energy state, and this quantum state is also known as what? Discrete energy state. Okay, so from this we can say that how many quantum state is there? How many quantum state is there within single crystal silicon? There is a 2 into 10 to the power 23 quantum state. Okay, so this many this many electron can sit within this silicon atom. Okay, so out of that, some of the quantum state are repeating and some of the quantum state are filled. Some of the quantum state are filled. So therefore, now we are confirmed about this energy level. Before going to discuss about Fermi Dirac probability function, why we want this Fermi Dirac probability function? Because actually what we want to realize the actual distribution of electron within the system, which is must to calculate the number of carrier concentration within the silicon crystal. Okay, so now we are going to discuss this Fermi Dirac probability function. Okay, so we are confirmed about this. What is energy level? What is quantum state? What is orbital? Where the quantum state is actually how many quantum state is there within a single energy level? Okay, so now see. So let us go for Fermi Dirac probability function. Okay, Fermi Dirac probability function or Fermi Dirac distribution function. Okay, so now we are confirmed about this. What is energy level? What is quantum state? What is discrete energy state? Where electron is what electron is sitting? Electron is sitting inside what? Inside the quantum state. Okay, so inside the quantum state. Now it makes some sense to discuss the probability density. What this Fermi Dirac probability function. Okay, so without discussing this, it is something nonsensible if we directly go to the discussion of Fermi Dirac probability function. Okay, so now see here. Now see what we are doing. So just take what one energy level. How many energy level? Take one energy level out of how many energy level is there? Total 5. Total 5 into 10 to the power 5 into 10 to the power 22. 22. Okay, so 22 atom is there. Atom per cube centimeter. Per cube centimeter. Okay, so this many energy level is there. Okay, because every atom has one energy level. Okay, one energy level, but that energy level we are seeing only outermost energy level. But this is what silicon atom. Yes, silicon atom, it has actually 3 energy level, but it has actually how many energy level? 3 energy level. This energy level has 2 electron, this energy level has 8 electron, and this energy level has 4 electron. But these innermost energy level are strongly bounded by nucleus. That's why we are not caring about this. Okay, so we are not caring about this, and we are just representing it as positive, means it is strongly bounded by this nucleus. Okay, so therefore we are concentrating only this outermost shell, because these are loosely bound electrons. So therefore we are focusing about this only. So this has what, one energy level. This is what, one single energy level. This silicon atom, how many atom? 5 into 10 to 10 to the power 22 atom. Okay, per cube centimeter, per cube centimeter. Just take one energy level. Okay, you just take one single energy level. We have taken single energy level. Okay, so let us take this. This is my E energy level. Okay, so give the name for this energy level as E. Okay, so this is my energy level E, and this energy level has what, some quantum state. Okay, so many quantum state is there. Let us say it has one quantum state, two quantum state, like this. This is my quantum state. This is my quantum state. See here, this is my energy level. Okay, so this is my energy level E. Okay, E energy level. How many quantum state? Like this: one quantum state, two quantum state, three quantum state, four quantum state, five quantum state, seven, eight, like this. So many quantum state, like n quantum state is there. Okay, n quantum state is there. Quantum state n means, let us take here some other number like G quantum state. G number of quantum state is there. Okay, now I have what, n number of particle. N is number of particle, number of particle, number of particle, particle, number of particle, or you can say it may be electron or it may be hole. Okay, it may be hole. Let us take it as electron. Okay, let us take this electron, this particle as electron. I have n number of electron. I have n number of particle, n number of particle as electron, and I have G number of quantum state. How many? G number of quantum state. Okay, so now see here, G number of quantum state. Now what is the probability that, take this, what is the probability that this particular, what is the probability that this particular quantum state, is filled by n particle, okay, what is the probability? What is probability? Actually every quantum state is occupied by single electron, but there is n particle, n electron, out of this n electron, out of this n electron, one electron will occupy this quantum state. Okay, this quantum state, but there is n particle, then what is the probability that this particular, take this particular quantum state here, what is the probability that this particular quantum state is occupied by this n number of particle as electron? Okay, what is the probability? This probability is nothing but probability of this n particle occupied into what, into this quantum state is proportional to e to the power minus kinetic energy of n particle divided by kt. So this is my actual, this is my actual probability. Okay, so this is what probability of n particle. Probability of this particular quantum state is occupied by what? Occupied by n particle. Any one particle can occupy this out of n particle, this particular quantum state. The probability is proportional to e to the power minus ke into n by kt. Okay, so n by kt, and this k is nothing but it is the kinetic energy of this particle as electron. Now see here, now we will focus that what, this quantum state has either electron is there, either electron is not there. Yes, electron is there, electron is not there, means electron is there means probability is 1, plus electron is not there, probability is 0. Okay, so then it is equal to what, 100%. Okay, so the probability of what, probability that the quantum state is occupied by the electron plus the probability that the quantum state is not occupied by the electron, is what, electron. Sum of this probability is equal to 100%, is equal to Oximo's probability. Okay, so this is what, 100%. Now see this. Okay, so here electron that may be occupied or not occupied by this quantum state, Okay, so it may be occupied, it may be not occupied. The sum of probability is 100%. What? 100%. Like that, let us say here, put here p is equal to, let us see this p of n. What? P of n. So this is my equation number 1. This is my equation number 2. equation number 2. Okay, so let us rub this. Okay, so remember this. Okay, so note down these two equation. So we will start from outside. Okay, so this is what probability that a particular quantum state is occupied by electron or not. Okay, or not occupied by electron. Hmm. Now see, now see here. This is what probability that a particular quantum state is occupied by electron is proportional to what? E to the power minus kinetic energy of that n particle divided by kT. Okay, so now this probability of n particle is equal to what? Is equal to, this is what probability of what? Probability that a particular quantum state, what quantum state? This quantum state. Okay, this particular quantum state, we have taken this particular quantum state. Okay, here electron is there, either electron is there or either electron is not there. Electron is there, probability is what? 1. Probability is p of 1. Electron is not there, probability is p of 0. Okay, probability is p of 0. Okay, so now for that p of 0 plus p of 1 is equal to what? 1 is equal to 1. Okay, so this is what? This is sum of the probability, that is 100%. Okay, so now this p of n, proportionality constant, let us assume that 1 by k, proportionality constant, take it as 1 by k into e to the power minus ke of n divided by kt. This k is nothing but energy of one particle, energy of electron. This what? This k is what? Kinetic energy of what? Particle as electron. Now, so this is my equation number. Let us take this equation number 2. Let us take it as equation number 1. Okay, so now probability that the particular quantum state is occupied by the electron is p of 1 is equal to 1 by k minus ke of 1 divided by kt. Okay, so divided by kt, this kt. Okay, so divided by kt. So this is my probability of what? Probability that a particular quantum state is occupied by electron. So this is my equation number 3. Okay, so now the probability that the particular quantum state is not occupied by electron is 0. That is 1 by k e to the power minus k kinetic energy of, this is what? 0 divided by kt. Okay, so this is my equation number 4. Okay, equation number 4. Now let us see from equation number 1, equation number 2. Okay, in equation number 2, let us see, this is what? P of n. Okay, p of n is equal to this is what? P of 0. First see p of 0, put this value into equation number 1. In equation number 1, we will get what? We will get p of 1 is equal to 1 by k e to the power minus k e of 1 divided by kt plus 1 by k plus 1 by k e to the power minus k e of 0 by kt. Yes, by kt is equal to what? Is equal to 1. Now 1 by k into e to the power minus ke 1 divided by kt plus e to the power minus ke into 0 divided by kt is equal to what? 1. Okay, so is equal to 1. Now we see the value of k from here is e to the power minus ke into 1 divided by kt plus e to the power minus ke of 0 divided by kt. So this is my value of k. Okay, so this is the value of k. Now see here, just what we will do, just put this value in equation number 1. Okay, in equation number 1, let us put this value in equation number 1, because we want to find what? We want to find this p of 1 is what? P of 1 is the probability that the given particular quantum state that is occupied by what? Electron, occupied by occupied by electron. So therefore P of what? P of 1 is equal to e to the power minus ke of 1 divided by value of ke is nothing but e to the power minus ke of 1, okay, of 1 divided by kt plus e to the power minus k of e into 0 divided by kt. Okay, so this is my value of p of 1. Okay, so let us take this term common. Okay, so we will get p of 1 is equal to e to the power minus k of e 1 divided by kt divided by e to the power minus k of e 1 divided by kt. Take this common. Okay, so we will get 1 plus e to the power what? Ke of 1 minus ke of 0 divided by kt. Okay, so this is what, and this will get cancelled. Okay, so this will get cancelled, and finally we will get here what? P of 1 is equal to 1 by 1 plus e to the power ke of 1 minus ke of 0 divided by kt. Okay, so this is what probability that probability that a given particular quantum state is occupied by electron. Okay, so just note down this, then after that we will see. So this is up to this. Okay, so p of 1 is equal to what is this? This is what indicating that a particular quantum state that we have taken this. Okay, so this is occupied by electron, that is p of 1 is equal to 1 by 1 plus e to the power minus ke of 1 minus ke of 0 divided by kt. What is this? K is nothing but it is the kinetic energy of a particle as what? Electron. Okay, so now see next. So let us see next. Next, as we know very well, what the total energy? Total energy is equal to what? Total energy is equal to kinetic energy plus potential energy. Yes, total energy is equal to kinetic energy plus potential energy, and therefore this kinetic energy is equal to what? Total energy minus potential energy. Total energy minus potential energy. Okay, so now see here, this kinetic energy is what? Function of what? N particle. What? N particle. Then this total energy is also a function of n particle. Okay, so function of n particle. Okay, so we will take it as a total energy only. Okay, total energy E minus U. So now see, first of all, ke of what? Ke of n as 1 means 1. This means what? This means the particle is there within the quantum state. In quantum state, particle is there means electron is there. If electron is there, then energy of that electron is E minus. This is my U of 0. This is my U of 1. Okay, so this is also a function of n minus U of n. Okay, U of n. Now ke, okay, ke of 1 means, this means that the particular quantum state is occupied by electron. Okay, which has energy E of 1 minus U of 1. Now see this, E of 1 is what? As energy E, and this minus U of 1 is what? U of 1 is nothing but this is my hypothetical energy. U of 1 is nothing but it is a hypothetical energy or imaginary energy. Okay, hypothetical energy, imaginary energy, but not real energy. And this hypothetical energy is represented by Fermi energy. Okay, so from here we can say that this Fermi energy is not a real energy, it is a imaginary energy, it is a hypothetical energy. Okay, so therefore this is my value of ke of what? 1. Ke of 1. Now this is my value of ke of 1 and ke of what? 0. Ke of 0 is equal to what? Ke of 0. If particle is not there within the quantum state, then what is energy? Wherever there is no electron, there is no energy. Okay, so there is no energy. So therefore by this, just put this value here, we will get what? We will get P of 1. P of 1 is equal to 1 divided by 1 plus e to the power ke of 1 is what? That is E minus EF by kt. E minus EF by KT. Okay, EF, E minus EF by KT. This is minus KE of 0 is what? 0. 0 is what? 0. So therefore, this is what? This is my probability that a particular given quantum state is occupied by electron. Occupied by electron. Or other way of defining this is what? P of 1 is nothing but it is n of E divided by G of E. G of E is equal to f of E is equal to 1 plus E to the power E minus EF by E to the power E minus EF by KT, E to the power E minus EF by KT. Okay, so this is what? This is my what? Fermi Dirac probability function. This is my Fermi Dirac. This is my Fermi Dirac probability Fermi Dirac probability function. Okay, Fermi Dirac probability function. Okay, so this is nothing but n of E means the number of quantum state, which is occupied by the electron out of the total number of quantum state present in energy E. Means what? This is my energy E. Yes, this is my energy, E level energy. So this Ne represent what? This energy N of E represent what? Number of quantum state. What? Number of quantum state. This represent what? N of E represented. N of E is representing what? Number of quantum state that is occupied by electron. Out of total number of quantum state. Like here, how many quantum state is occupied? 1, 2, 3, 4. Means 4 divided by total how many? Like n means G number of what? G number of total number of quantum state is how many? G, like G in energy level E. Okay, both are function of what? Energy. Okay, so this means what? This. Okay, so P of 1 is equal to N of E by G of E is equal to F of E is equal to 1 by 1 plus E minus EF by KT. Okay, so therefore from here what we can say? What is Fermi Dirac probability function or Fermi Dirac distribution function? What define this? This define that the probability that a particular given quantum state is occupied by electron. Okay, so it define the probability that given quantum state is occupied by an electron. A particular given quantum state is occupied by an electron. Okay, so that is equal to 1 plus E to the power E minus EF by KT. Or another way we can define it as it is the ratio that the number of quantum state that has occupied by electron out of the total number of quantum state in energy level E. Okay, so this is what exact definition or exact derivation of for this Fermi Dirac probability function. What we did first, we took one energy level, and we took what number of quantum state in energy level. Okay, so then after that we select one particular quantum state. Then after that we found that if either this particular quantum state is occupied by electron or not. Okay, for that we found what probability that this particular given quantum state is occupied by electron or not. Okay, that probability is equal to 100%. Okay, so like that, and we have one particular definition that the given quantum state is occupied by n number of particles. For that, P of n is proportional to e to the power minus ke e to the power minus ke of n divided by kt. Okay, so from this definition now we are understood that what is the exact meaning of this probability, this Fermi Dirac probability function. Okay, Fermi Dirac probability function tell us about that it determines the probability that the given quantum state is occupied by an electron. Given quantum state is occupied by an electron which is present in energy level E. Or another way it is defined as the ratio of the number of quantum state that is occupied by electron out of the total number of quantum state that is present in the energy level E. Okay, energy level E. So this is about this is about the just definition of what definition of Fermi Dirac probability function. Now after that we will see the what the characteristic between the distribution function and energy for different temperature. Okay, at absolute 0 degree temperature, at temperature greater than 0 degree temperature. Okay, so from there we will see how the characteristic change by temperature. Okay, so that's all for this lecture. That is about just the definition of this Fermi Dirac probability function. Okay, so that's all. So this is part one for this Fermi Dirac probability function, and it is the topic. It is the topic under the chapter of what under the chapter of semiconductor under thermal equilibrium. Okay, thermal equilibrium. Thermal equilibrium in the sense there is no external force that is acting on the semiconductor device. Okay, so this is my then the semiconductor is under thermal equilibrium. Okay, so that's all for today. This topic, this lecture. Thank you very much. Okay, thank you.